This is Professor Jodi Cooley from Southern Methodist University, and today I will be giving a lecture on 2D motion. Before I begin, I'd like to make a couple of announcements. First, remember that in order to receive full credit on your homework, you must use the homework guidelines. This means that each page of your homework should contain your name, date, and page number. 3 p.m. Friday is a hard deadline. Late homework will receive a score of 0. The Chapter 4 homework is due Friday, February 11th, and we will have an in-class quiz covering Chapters 2 through 3 on Tuesday, February 8th. I'd like to revisit the Coke bottle problem from the last class. If we recall, we had a situation where a plane was flying overhead and dropped a Coke bottle which hit a man in the head who was standing on the ground. In this case, for this problem, it doesn't matter if you pick your origin, your y equals 0 point, to be the ground or be the plane. In both cases, delta y is equal to minus 1,000 meters. If you also remember, in the solution, we ended up solving for v sub f. And if we chose to use the kinematic equation, v sub f squared equals vi squared plus 2a delta y, because we were taking the square root of the velocity, we ended up with two solutions, one positive and one minus. In this case, it is important to decide whether or not your final answer should be the positive or negative solution. And since in this case we know that the bottle is moving in the negative y direction, we know that the velocity must be negative. So the correct answer is v final equals negative 140 meters. In order to receive full credit for this problem, you must get the direction correct. Up to this point, we have been talking about motion in one dimension. And we had defined velocity is the change in position over the change in time, or the displacement over time, dx dt. And acceleration was the change in velocity over time, or the second derivative of the change in position over time. And we also had defined 4 kinematic equations of motion, which we were calling EOM, equations of motion. We had 2 equations for the position of an object, and we had 2 equations for velocity. What we're going to do today is extend these equations and these ideas to 2 dimensions. So the first thing that we need to do is develop some vocabulary. The first term that we're going to define is the position vector. This describes the position of an object in 2D. For example, the position vector for point A on this plot starts at point 0 and goes here to point A. This is the position vector. The displacement vector describes an object's change in position. And so delta r in this case would be r final minus r initial. So the displacement between point A and point B would be described by this vector, vector r, which is the difference between the position vector r final and the position vector r initial. Following the approach we use for one-dimensional vectors, we can define an average velocity. Average velocity in 2D is defined as the displacement over time. Notice velocity is a vector and the displacement is a vector. In this equation, time is a scalar. In the same way that we define instantaneous velocity in one-dimensional motion, we can define instantaneous velocity in 2 dimensions. The way we do this is that we take the limit as delta t goes to 0 of delta r over delta t, and this gives us dr dt. The instantaneous velocity is given by the line tangent to point A. For acceleration, which is the rate of change of the velocity with respect to time, we just can do the same thing. Again, acceleration is a vector, the velocity is a vector. So if we take a look at this plot of displacement, at point A we have an initial velocity, and at point B we have a particle at its final velocity. If we want to find the change in velocity, we just take the final vector and we subtract from it the initial vector, and what we end up with is the change in velocity vector. We can also find an instantaneous acceleration, and again, to do this we use the same trick. We take the limit as delta t goes to 0 of delta v over delta t, and this gives us the derivative of the velocity with respect to time. I want you to note that there are three ways we can get an acceleration. We can change the magnitude of the acceleration, we can change the direction of the acceleration, or we can change both the magnitude and the direction. So as an example of this, let's think about the movement around a circle. So let's say we have a circle where we have a displacement of vector 1 and we have a second spot 2 here. The displacement here is given by delta r, which is the hypotenuse of this triangle. At point 1 we have velocity vector v1 and it points towards the right. At point v2, point 2, we have a velocity vector which has the same magnitude as v1 but is pointed in a different direction. So in this case the magnitude of the velocity is constant, but the direction of the velocity changes. So the object must have an acceleration. Motion in two dimensions must be treated as consisting of two independent motions, each in one of two perpendicular directions. The only factor that these two directions have in common is time. So in that case, for position, we must divide the vector up into its x or I hat and y or j hat components. So vector r is equal to x in the I hat plus y in the j hat direction. Similarly, the velocity, which is equal to the derivative of the change in position with respect to time, would need to be divided into its x and y, or I hat and j hat components. So that is really equal to dx by dt in the I hat plus dy by dt in the j hat direction. Or a different notation that we will commonly use is that vector v is equal to v sub x in the I hat direction, so the x component of the velocity, plus the y component of the velocity in the j hat direction. Acceleration follows the same pattern. It's a vector. It has an x component, a sub x, that's in the I hat direction, and a component a sub y, that's in the j hat direction. In addition, we must also apply these same rules to the kinematic equations, or the equations of motion as we've been calling them. They must be applied separately in each direction. So, for example, one of our equations of motion says that the final velocity is equal to the initial velocity plus at, and here you see it in its full vector form. If we were trying to use this equation to solve a problem, we would need to solve separately for the x and y directions. So this equation would be broken into its x component and its y component. And if we wanted to put this back together, that means that the final vector is equal to the x component plus the y component. The same rules would follow for the position equation of motion. So we have here r is equal to ri plus vit plus 1/2 at squared in its full vector form. However, if we needed to use this equation ever to solve a problem, we'd have to break it into its x component. So x final equals x initial plus v initial in the x direction times t plus 1/2 a, the acceleration in the x direction, times time squared, and into its y component. So y final is equal to its y initial position plus the velocity initially in the y direction times time plus 1/2 the acceleration in the y direction times t squared. Let me just make a few notes here on kinematic variables. Kinematic variables along the x-axis affect only motion along the x direction. Similarly, kinematic variables along the y-axis affect motion only along the y direction. The only factor common between the x and y directions is time. Consider the motion of a projectile. For example, let's say we throw a baseball into the air at an angle theta to the horizontal. The initial velocity of the baseball can be broken down into its x and y components. The x component of the velocity can be found using trigonometry. The x component is equal to the magnitude of the initial velocity vector times the cosine of the angle in between. The y component of the initial velocity is similarly equal to the magnitude of the initial velocity vector times the sine of the angle in between. The equations of motion for the position of the baseball as a function of time would also need to be broken down into its x and y components. For the x component, we have the x final position is equal to the initial x position plus the initial velocity in the x direction times time plus 1/2 the acceleration in the x direction times t squared. The final y position of the baseball would be equal to the initial y position plus the initial velocity in the y direction times time plus 1/2 the acceleration in the y direction times time squared. So now I ask you a question. Neglecting air resistance, what is the acceleration in the x direction for a projectile? Is it A, 0, B, depends on the situation, or G, 9.80 meters per second squared? The answer is 0. This is because if we neglect air resistance, the velocity in the x direction is always constant. So the initial velocity is equal to the final velocity. Hence the change in velocity is equal to 0. Hence the acceleration is equal to 0. A second question. If we neglect air resistance, what is the acceleration in the y direction for the projectile? Is it A, 0, B, does it depend on the situation, or C, is it equal to negative 9.8 meters per second squared? The answer is C. The acceleration in the y direction is equal to the gravitational acceleration. Let's use this information to simplify our equations of motion. So let's start with our equation of motion for velocity. We know that the final velocity is equal to the initial velocity plus a times t. So let's take a look at the x component. That means that the final velocity in the x direction is equal to vi times cosine theta, which is the initial velocity in the x direction. However, we don't have a contribution due to acceleration because we know the acceleration in the x direction is 0. In the y direction, we know that the final velocity will be equal to vi sine theta, which is the initial velocity in the y direction, minus g times t. This is because our acceleration in this case is equal to negative g, the acceleration due to gravity. For position, we have r is equal to ri plus vit plus 1/2 at squared. Again, if we're looking at the x direction, we have no acceleration, so this term drops out. So our final x position is equal to our initial x position plus vi times cosine theta times time. In the y direction, this means that our final y position is equal to y initial plus vi sine theta times t minus 1/2 gt squared. Again, the acceleration in the y direction is the gravitational constant, which is equal to negative g. So let me ask you a question here. Why is it that when we throw our baseball up at some angle theta that it doesn't leave the earth? What stops the motion? The answer, the ball hits the ground. Remember, both the horizontal and vertical directions have time as a common factor. The vertical motion is changed by the presence of the acceleration in the y direction. So let's examine this a little bit more carefully. Here we have a cartoon of a projectile path, and we're going to examine the motion at points A, B, C, D, and E along the path. So initially, at point A, the time is equal to 0. So what we have is we have a projectile or a particle, or our baseball if you will, given with some initial velocity. So we can find the initial velocity in the x direction, and we can find the initial velocity in the y direction of this trajectory. In the x direction, it's just VI cosine theta, again using trigonometry, and in the y direction, it's just VI sine theta. So what happens when we move to time b? As time changes from TA to TB, the vertical component of the velocity changes. So that would be the vertical component in the y direction. The velocity in the x direction does not change. It is constant. So it is still equal to VI cosine theta. But in the y direction, the velocity has changed. It's decreasing because of the presence of an acceleration due to gravity. In this case, at time TB, the velocity in the y direction is equal to VI sine theta minus g times TB. So what happens when we get to point C? At point C, the y component of the velocity is 0. We are at the peak of the path of the projectile, and it no longer moves in the y direction. The velocity in the x direction is still constant. So we know that the velocity at point C is equal to 0, and this is equal to VI sine theta minus g times TC. And we can solve this equation and get an expression for how long it takes the projectile to get from point A, t equals 0, to its peak in the path. And that is equal to VI sine theta divided by g. At point D, the velocity in the y direction becomes negative, and eventually, when we hit point E, the projectile hits the ground. Just before the projectile hits the ground, I should note that the x component of the velocity is still constant, is still equal to VI cosine theta. Now let's derive an equation for the maximum height obtained at the peak of the motion of the projectile. This happens when t is equal to tc. So we start with our equation of motion for position. Y final is equal to y initial plus velocity, the initial velocity in the y direction, times time, plus 1/2 acceleration in the y direction times t squared. We are looking for h max, which occurs when the position is yc. So that's just equal to y initial plus vi sine theta, which is the y component of the initial velocity, times tc minus 1/2 gtc squared. Here we've substituted in also the acceleration in the y direction, which is negative g. Then we just plug in what we know. We know the initial y position is 0, and then we plug in our tc term, which we derived in a previous transparency for t, and similarly we plug it in also over here in the t squared term. Then we just do some algebra and we find an expression for h max, which is equal to 1/2 the quantity v initial squared sine squared theta divided by g. We have already seen in 1D vertical motion that the motion is symmetric, meaning the time up equals the time down. The same rule applies here in 2D motion. The time that the projectile takes to go up is the same as the time that the projectile takes to go down. That means that the total time traveled, TE, is equal to 2 times TC. So this is equal to 2 VI sine theta divided by g. Now let's focus on the x direction. The total distance traveled in the horizontal direction is called the range. The range is equal to x final minus x initial, which is just equal to the initial velocity in the x direction times the time traveled, TE. So if we take and substitute in for TE, our expression from the previous page, what we find is that the range is equal to VI cosine theta, which is just an expression for the initial velocity in the x direction, times 2 VI sine theta divided by g. If we do a little bit of algebra and simplify, we find that the range is equal to VI squared divided by g times sine of 2 theta. Note here, this is sine of the quantity 2 times theta. This is not sine squared theta. Because of the symmetry of the sine function, the range for theta is equal to the range for 90 minus theta. So as an example, let's take a look at this plot. Let's see what is the range for a trajectory of 30 degrees on this plot. We find that to be 225 degrees. If we take 90 minus 30, we end up with 60. And if we look at the projectile range for an initial angle of 60 degrees, we find it too also has a value of range of 225 meters. Again, this is just a relationship of the sine function. Now let's do an example. A firefighter a distance d from a burning building directs a stream of water from a fire hose at an angle theta I above the horizontal as shown in the figure below. If the initial speed of the stream is VI, at what height h does the water strike the building? And we are given a hint. We should use the equations of motion to find an expression for the time the water is in the air. And then we should solve for h using a second equation of motion. So looking again at our figure, what we're given is we're given initial velocity of the water, we're given the angle that the hose is initially aimed in, and we're given the distance between the firefighter and the building. What we're looking for is h. This is an example where we would use the x direction in order to find the time variable, and since time is the constant between both the x and y directions, we can then take that variable and substitute it into an expression for the y direction. We will use the expression x final equals x initial plus 1/2 vxi plus vxf times t. X final minus x initial is just the displacement d. In the x direction, the initial velocity is equal to the final velocity, so the quantity in the parentheses is equal to 2 vxi. If you multiply that times 1/2, that just leaves you with vxi, and then of course you bring the t down. So we have an expression d is equal to vxi times t. We know that the initial velocity in the x direction is equal to the magnitude of the velocity vector initially times cosine theta I times t. We solve this expression for t, and we end up with t is equal to d divided by the quantity vi cosine theta I. And I mark this equation as number 1. So now we will use number 1 in another equation of motion to find the height. We can use the kinematic equation of motion for the y position. Y final is equal to y initial plus the initial velocity in the y direction times time plus 1/2 a in the y direction times t squared. Since we're looking for the height is the displacement in the y direction, y final minus y initial. This then is equal to vi sine theta I, which is just the initial velocity in the y direction, times the expression for time that we have found in number 1, minus 1/2 g times the time expression from number 1 squared. We do a little algebra and we end up with h is equal to d tangent theta I minus the quantity gd squared divided by the quantity 2 v initial times cosine theta I. We will conclude the lecture today by talking about circular motion. Uniform circular motion is the description of motion with constant speed on a circular path. The magnitude of the velocity is constant, but the velocity vector is continuously changing. Even though the particle on the path is moving with constant speed, it does have an acceleration. The velocity is changing. So how does the acceleration look? To answer this question, we must examine the velocity. Remember, the acceleration is equal to the change in velocity over the change in time. In this picture here, we have a plot of the linear velocity at 2 points on a circle. We have a particle that is moving from point A to point B with uniform circular motion. This means the magnitude of velocity vector at point A is equal to the magnitude of the velocity vector at point B. The difference in the velocity vector is equal to the final velocity vector minus the initial velocity vector. Just rearranging terms, this means that v initial plus delta v is equal to v final. And so if we look at this graphically, we can see that the vector is changing direction. And the direction of the change of this vector is towards the center of the circle. The velocity vector is tangent to the position vector. Here we have Ri, Vi, these are tangent. The velocity vector is tangential to the position vector. Thus, the vector v and the vector r are perpendicular, and this is true at any point around the circle. Thus, the triangles defined by vector Ri, vector Rf, and vector delta r, and the triangle defined by vector Vi, vector Vf, and vector delta v are similar. Each side of one triangle is perpendicular to a corresponding side of a second triangle. So from the rules for similar triangles, this tells us that the ratio of the sides are the same. So delta r over r is equal to delta v over v, where here I've adapted a notation that r is equal to the magnitude of the initial position vector, which is equal to the magnitude of the final position vector. And again, for velocity, v is equal to the magnitude of the initial velocity vector, which is equal to the magnitude of the final velocity vector. So all we need to do is solve for delta v. So solving for delta v, we find that the magnitude of delta v is equal to v over r times delta, the magnitude of delta r. We know from the definition of average velocity that the magnitude of the average velocity is equal to the magnitude of the change in the velocity vector over time. If we substitute the expression we found for the magnitude of the change in the velocity vector into our definition for average acceleration, we find it's equal to v over r over delta t. If we then take the limit as delta t goes to 0, we end up with the expression that the average acceleration goes to v over r dr dt. We know that dr dt is equal to the instantaneous velocity. So this gives us v over r times v, which is equal to v squared times r. This quantity is known as the centripetal acceleration. AC is equal to v squared over r. Centripetal means center seeking. Notice the centripetal acceleration is a magnitude. There are two other quantities that we need to be familiar with when we're talking about circular motion. The first is the circumference of a circle. Let me remind you that the circumference of a circle is the total path around the edge of a circle, one revolution. The circumference is equal to 2 pi times the radius of the circle. The second quantity that we will need to know about is period. Period is equal to the time it takes for a particle or object to make one revolution around the circle. The period t is equal to 2 pi r, where r is the radius of the circle, divided by v. So let's look at an example. What is the centripetal acceleration of a person located on the Earth's equator due to the Earth's rotation? The radius of the Earth is 6.37 times 10 to the 6th meters. In this problem, we are asked to solve for the centripetal acceleration. The centripetal acceleration is equal to v squared over r, so we need to find an expression for v. The magnitude of the velocity is equal to delta x over delta t. The displacement delta x is equal to the circumference of the Earth at the equator, 2 pi times the radius of the Earth. And the time that we're talking about in this case corresponds to the period t, 1 day. If we substitute our expression for velocity into our definition of centripetal acceleration, we find that the centripetal acceleration is equal to 2 pi radius of the Earth divided by the period squared times 1 over the radius of the Earth. Note here that the period t is 1 day. In order to perform this calculation, you will need to convert days into seconds. If you plug the numbers in and work this out on your own, you will find that the centripetal acceleration of a person standing on the Earth at the equator is 3.37 times 10 to the minus 2 meters per second. Note that this is 0.003 Gs, where G is equal to 9.80 meters per second, the gravitational acceleration. So I pose a question to you. What is the centripetal acceleration of a person standing at the North Pole? In this case, the radius that we're talking about is 0. So what we need to do is we need to take our expression for the case that the radius of the Earth is going to 0. So what we find is then that the centripetal acceleration is 0. Up until this point, we've been considering the specific case of uniform circular motion. Now I ask you to consider the general case. Motion can occur along any curved path and does not have to happen at constant speed. And so our acceleration vector is described by a radial and a tangential component. In this slide, we see the motion of a particle along the curved path. Notice that the velocity changes in direction and the magnitude of the velocity change in direction. Let's look more closely at the components of acceleration. The tangential component of the acceleration is equal to dv by dt. The tangential acceleration is responsible for the change of speed of the particle. It points tangent to the path of the particle along the velocity vector. Radial acceleration is responsible for the change in direction. It does not change the speed. The radial acceleration is equal to negative v squared over r. Note that the radial component and the tangential component of the acceleration vector are perpendicular to each other. Thus, the magnitude of the acceleration vector is equal to the square root of the radial component squared plus the tangential component squared. I'd also like you to note that the radial component of the acceleration is equal to the opposite of the magnitude of the centripetal acceleration. The negative sign here indicates the direction of the radial component of the acceleration. The negative sign means that the radial component is pointing inward. That's all that I have for today. I look forward to seeing everyone in class on Tuesday.